My name is Andrew Lindell from Aladdin Knowledge Systems and Bar Ilan University in Israel. I'm going to talk about anonymous authentication, something which is a contradiction in terms, but we'll see that it's one that can actually be fulfilled. I'm going to start with something completely different, which is just going to be motivation, really, for why we would want anonymous authentication. I'm going to talk for a few minutes about chat rooms. I think there's something wrong with the mic. I'm going to talk about chat rooms, which, as everyone knows, have been a huge success for youth, but at the same time, for anyone who's a parent, it's a huge concern for parents. And why is that? Based on a recent survey by actually a very serious research institute called the Crimes Against Children Research Center, they discovered that 34% of children received unwanted sexual solicitations over the internet, and many of those through chat rooms. What's perhaps even more scary is that 4% of all children received sexual solicitations that went beyond something online and were actually through some sort of physical or at least offline contact, maybe calling them over the telephone or sending them a package or actually trying to physically meet them. That's 1 in every 25 children, so that's a very, very scary thought. At first, we might think, well, why is this happening? Firstly, chat rooms are supposed to be anonymous. So firstly, why would it bother us so much in any case that online sexual solicitations are taking place? Well, obviously it's disturbing to the children, but beyond that. And how do we get that 4% actually become offline? And there are two reasons for this. The first is that approximately a third of the children that were interviewed actually posted personal information online. They had no awareness there was actually a big problem to do such a thing. And what's even more concerning is that even when children or users are aware that they should not be posting personal information, with very little work it's possible to actually find their real persona. Another example of this is what's happening with college students in social networks, where even if they're responsible and not actually posting their personal information, they talk very freely about what they do, about their college experiences, where they took drugs. And prospective employers are now actually searching the internet to do background checks on potential candidates. And there are a number of employers who've explicitly stated they saw that a certain person had posted at a social network that they had done something inappropriate during their college years, which I assume that many, many people actually have also done, and therefore didn't give them the job. So the first lesson is that people are unaware of the fact that they shouldn't post personal information, but even when they don't, when they are aware, it's actually very easy to find it. For example, some people might use their Yahoo ID in their social network or on the chat room, thinking that just from that ID that they can't get to them, no one can get to their real persona, but it's actually very easy by going through Yahoo. So these issues are really, really problematic, and they're becoming more and more so. What are the solutions? Well, there's no actual solution, no full solution. We can look at a number of different things. First and foremost, education. People have to to understand that what they post and what they say is not private. It's very, very not private, and can also actually often get back to them. Parental control when we're talking about children, obviously law enforcement, and the type of solution I'm going to be referring to here, and what's a double-edged sword, is the technological solution. So one proposal is to set up safe chat rooms that require authentication. And we'll give these authentication devices to high school students. VeriSign had a project like that, and they were going to use one-time passwords. They gave out OTP devices, set up safe chat rooms, and in that way we would hopefully prevent pedophiles from getting into the chat rooms because they wouldn't have the authentication device. Now this solution is actually a little bit problematic. I mean, it has its downside as well. If the children now think that anyone inside that chat room can be trusted, then if someone does manage to get in, say steal an OTP device or in some other way, then it can be a bigger problem. But definitely as a first step, it's something which makes a lot of sense. Other suggestions have been to use perhaps a biometric device which actually measures that the person who's wearing it is a child, and then allow access. So there are a number of possible solutions which are running around authentication, and it sounds like a very, very good first step, and I think it is a very good first step where it's possible, but now it opens a whole new can of worms. One of the most attractive properties of these chat rooms is anonymity. Children, teenagers, even college students are under immense peer pressure. And often in their real world life, they can't say exactly what they want. They can't speak freely. They're afraid of the ramifications. So they go online. And online they can act freely, speak their mind. Of course, they can also use this badly, but in a positive way, they can actually be themselves. They can ask advice on sensitive issues and feel that it's not going to come back to them. But once we make them authenticate, once we make them sign up for an authentication device with their real name, and we give them something physical, and they have to use that physical device in order to get into the chat room, then all their anonymity is lost. Now you might say, okay, but the website, the web server, the service who's running this chat room, this safe chat room, doesn't have to publish who the user is. But that doesn't make any difference, because we know that inadvertently often information goes out. Even if we trust that service, that they don't want to leak our information, do we really believe that it's safe and no one can get to it? Once we have to go through that step of physically authenticating, we start having doubts. And we may not also completely trust them. So in order to protect ourselves, we're giving up on something else which is very important. And of course, we don't want to do either. We do want to protect our children, but we also want to have privacy. And that's where anonymous authentication comes in. It's a contradiction in terms, because authentication and security in general is all about knowing exactly who is in our network, exactly who's coming, and why they're allowed in. Do they have the permissions? What permissions do they have? When did they come into the network? When did they leave the network? That's what security is all about, and that's what authentication is all about. So how can I talk about authentication without knowing who the user is? It seems like nonsense. But if we think for a minute, we realize that authentication isn't necessarily about knowing exactly who the user is. It's about knowing what their permissions are. It's just about knowing whether they're allowed in or they're not allowed in. Of course, if there are personal permissions, then that's something different. But if we're talking about some sort of web service that you have to subscribe to, then all the server really needs to know is that this person has subscribed. This person is allowed in. It doesn't care exactly which user it is. It doesn't make any difference. And the idea of anonymous authentication is that the user will authenticate to the server, and the server will be convinced that it is an authorized user, but it will not know at all which authorized user it is. Of course, the first question is that really possible? It sounds very difficult. Of course, the answer is yes, otherwise I wouldn't be here. So I'm going to talk mostly about that today, how we can actually build such a system. Before I go further, I'd like to give a couple of other applications beyond the chat room. Professional forums today are becoming very popular. I can go, if in my research, I can download papers. I can ask questions. I can discuss technical issues. They're used by researchers, developers all the time. What we don't necessarily think about is that they're also a great source of industrial espionage. Because if someone looks at what papers I'm downloading, what I'm reading, what I'm asking, what I know to answer, they can actually know a lot about what I'm working on. If I'm working on some secret project, some new product line, then just by looking at what I'm interested in, it's possible to guess what it is that I'm trying to do. And that can be, of course, of great advantage to a competitor. So one possibility is to use anonymous routing, which I'll talk a little bit more about later on. But what happens if this service needs registration or even payment? I'm not going to register from scratch each time. It's impractical. It's time-consuming. If it needs payment, even more so. We need to authenticate to this service. Then again, once I'm authenticating, I'm caught, and anyone who wants to try and get my information, or at least the service knows my information, and it's something which I want to try and avoid, I'd like to have anonymous authentication. Two other possible applications. One is whistleblowing. We want to make sure that an employee can really report something without ramifications. And unfortunately, even though the law says that you're not allowed to take revenge upon an employee who's a whistleblower, it happens in practice. And so we'd like to allow any employee to report, but we want to make sure that it's actually an employee, that it's not someone else who's just coming along and reporting something that they don't really know anything about. So again, we'd like anonymous authentication. Social networks I talked about, we want to prevent those employers from using the social networks of college students as a source of information for background checks. If we need authentication on those sites, then again, we'd like anonymous authentication. Another issue that I'm going to talk about is revocable anonymity. Because, well, first of all, let's be clear, we don't always want anonymity at all. If I'm talking about my organizational network, my private network at work, we don't want anonymity at all. We need to know exactly who's there. Anonymity is for other purposes, for, say, websites, for my what I'm doing online, for exactly the examples I gave beforehand. But even here, even when I want anonymity, sometimes I want to limit it. Because let's think about the case that I do use anonymous authentication, and consider the case that one of the users is harassing others. So what I'd like to do is simply cancel their account. But I can't because I don't know who they are. I'm talking about using anonymous authentication protocols that provably protect, cryptographically protects the user, guarantees the user that it's an anonymity. So once I'm doing that, then the server has no way of knowing who it is that's harassing the others. So we'd like to sometimes be able to revoke anonymity, for example, through some court authority. The court authority, through a court order, could revoke anonymity, but no one else can. And again, cryptographically it's protected, so nobody else can, even if they want to. Even if they want to bypass. It's not like wiretapping where you supposedly need a court order, but you could do it without that. You'd just be breaking the law. Here, without that court order, you wouldn't be able to do it all because that court has some secret key which enables it to revoke anonymity, and nobody else knows the secret key. That was the outline for my talk. I'm going to start by talking about privacy in general and why it's important. You may be thinking, well, everybody here at Black Hat believes that privacy is important. I don't have to convince anyone. What I'm going to try and do is give a much more concrete perspective on privacy. Often people feel that privacy is important for very vague reasons. I want to be very, very concrete because our understanding of why privacy is important has great ramifications on the solutions we provide. Sometimes we give privacy-preserving solutions which actually don't solve the problem at all because we have a misunderstanding of what the dangers of a loss of privacy are. I'll then talk very, very briefly about anonymous web surfing, and I'll be very brief here because there are a lot of other talks in this track that are going to focus on it, and I'm going to use it only as an infrastructure. I'm going to assume that it exists. And then I'll go into anonymous authentication in detail, define what it means, what I'm asking for, and show how it can actually be achieved. And then I'll talk about some extensions to revocable anonymity and other things as well. So let's talk about privacy again from a concrete perspective. So as I said, everybody here agrees that privacy is important, but why? If you ask the average person on the street, even one who really believes that privacy is necessary and important, they don't really have a good answer as to why. If you push them and if they think for quite a bit, they'll tell you that it's an invasion into their personal space. So if I had an argument last night with my wife, and everybody in my neighborhood heard the argument and knows about it, even though I wasn't expecting that to happen, I feel that that's an invasion into my personal space. Because it happened within my four walls, and somehow what happened within my four walls, within my personal space, went out. And that's a loss of privacy. Warren and Brandeis termed it the right to be let alone. Simply the right to be let alone. It's a personal feeling. It's really an emotional issue. What I'm talking about is feelings. Because to be honest, so what if everybody knows that I had a fight with my wife last night? Many people have fights with their wives, or probably most people have fights with their wives and husbands at some stage. It doesn't really make much of a difference, at least not concretely. So what's really the problem? What concrete damages can be occurred from this loss, from this invasion into my personal space? And again, I want to focus on concrete damages and not just on emotional issues because they have actual ramifications. We want to construct secure solutions to these problems. a concrete damage that comes just from, and I'm going to talk about more issues later, that comes just from this invasion to my personal space, is that of self-censorship. Once I know, or I believe, or I fear that what I'm doing online can be traced back to me, I automatically start behaving differently. So it's inhibiting my free speech without necessarily anybody, it's obviously not legally, no one's forcing that inhibition of my, that limitation of my free speech. But I automatically will start censoring myself when I know or when I fear that what I'm doing online can get out. And here are a few examples. Teenagers on chat sites, we talked about that beforehand. Universities often have forums where students can comment on courses and on lecturers. Now, we'd like the students to be respectful, but we'd also like them to be able to speak honestly, because that's important information for us. But if the students fear that if they say something bad about a lecturer, it's going to get back to that lecturer, then they're going to be afraid to do it. So we'd want, that's also an example of self-censorship. But I think one which I most identify with and I most fear is the limitation on how we use the internet for important information. So there are a lot of sites which I'm doubtful about how reliable the information is there, but there's a lot of very, very important and good information. Medical information. A lot of universities have places where students can post questions about sexual diseases, sexual practices. And it's very, very important that teenagers, college students, and other people, and older people also, can search for medical information, for example, in a private and anonymous way. If all of your Google queries were published, then you would be querying very different things, and you would it's quite clear that you would stop searching for sensitive information, even though it's very beneficial to you. So the first concrete damage is that of self-censorship, and it's one that is, of course, very severe, but it's only a problem if my online behavior, if my online profile can actually be linked to my real-world identity. Because I'm Andrew Lindell, but when I'm online, I'm an IP address. Okay, so somehow that link has to happen for it to be a problem. Because if the neighborhood knows that someone in the neighborhood had a fight with their wife last night, then of course it wouldn't bother me whatsoever. And this fact that the link is what the problem is actually widely held, it's widely believed. In a poll in 2000, 35% of people said that they were not at all comfortable with profiling their online information, even if it wasn't linked to their real-world identity. So just the mere profiling bothered 35% of people. But when they were asked if that profile would be linked to their real-world identity, the number jumped to 81%. So a vast majority of people are very concerned about profiling, especially when it's linked to their real-world identity. It's my guess, and it's pure speculation, I admit, but it's my guess that 35% who said that they were concerned, even if it wasn't linked, are really concerned because they fear that it may be linked in the future. I agree that it's speculation, but that's what I would guess. In any case, there's a very big gap between linking and not linking in terms of how people feel. So it seems that if I don't link my information, then everything is fine, because no identifier means no invasion of space. Again, if it's 100% guaranteed that a user's profile can never be connected to their identity, and let's assume we have a magical mechanism for guaranteeing that, then we're not going to suffer from self-censorship. What I'm going to try and do now is to convince you that this is a very naive perspective on privacy, and in fact, even if linking does not take place, we can be in very big trouble. Let's look at the example of an online newspaper, a personally tailored newspaper. Okay, it's something which is a very nice idea. It's been thrown around a lot. Everyone has different interests. They're interested in reading different articles. What about having an online newspaper that when I open it in the morning actually presents the articles that are of interest to me? How will it know what interests me? Well, firstly, I can fill in a questionnaire before I start the service. But more importantly, or more interestingly, it can use data mining to learn what I'm interested in by looking at what articles I read, how long I spent on them, in what order, at what time of the month or the year, compare that to other users as well, and build up profiles on what my interests really are when I come to look at a newspaper. And it can give me a tailored newspaper. It's a great idea. However, if we say that our garbage says a lot about us, and it does, right? If someone went through all of our garbage, they'd learn a lot about information about us. What we read in the newspaper says even more. Our political interests, what stocks we're interested in, what our hobbies are, what companies we follow, religious beliefs. A lot of different things can be found in what we read in the newspaper. I don't necessarily want the newspaper to know all of that about me. I don't want that information out there. I don't want it profiled. Now, if my identity is never provided, once again, it seems like that's fine. But this is completely false. Based on this belief that the linking is not the only problem, if I had a basic pseudonym that wasn't linked to me, that couldn't be linked to me, then everything would be fine. Let's look at now a concrete problem that could occur even if linking never occurs. The user's profile, as I said, reveals a lot about them. So a newspaper with strong interests could now tailor content to that user. Not just to give them the articles that they're writing in a certain order of what they're interested in, but could also try to actually manipulate them based on their interests. You know that if you're having an argument with someone, a debate with someone, and you know a lot about them, about what they believe and they don't believe, about what their interests are, then you can push a lot of buttons. And if they don't know the same things about you, then you have a significant advantage. So this might sound a bit Big Brother-ish, but it's a real possibility. The newspaper could use its knowledge about you against you without you even being aware that it's doing that. Right? I know that every newspaper has certain political biases, but I also know that everybody's reading the same thing, and here I'm being given something different and not even knowing it. This is something which privacy advocates talk about. It's an infringement on a person's autonomy, because your information can be used against you to manipulate you. And even if I have a pseudonym, it doesn't help whatsoever, because all that's necessary is to manipulate the user standing behind the pseudonym. The newspaper doesn't care about my name, Andrew Lindell. It doesn't matter whatsoever. It's not a matter of knowing about me. It's about using my information. And this is something which most people haven't thought about when they think about privacy concerns. They think about what happens when someone knows information about me. But I'm talking about something completely different, which is what happens when someone can use my information against me. It's a completely different world. Again, industrial espionage. They may not know that I work for Aladdin Knowledge Systems, but they can know that some competitor is interested in researching that product, is developing that product. That in itself is less damaging, but it can still be damaging. Price discrimination, a similar thing. Knowing my personal interests, the way I shop, that maybe that I don't shop around, that I don't look for cheaper prices, I can be discriminated against in an unfair way. That's a whole big debate because economists actually like price discrimination. Consumers don't. When is it fair? When is it unfair? We won't go into it here. So in conclusion of this part of the talk, privacy is much more than being let alone. It's not just a matter of my information going out, but it's about it being used against me. And naive solutions that rely on a pseudonym just don't suffice. What we need is unlinkability between transactions. We need that the different actions that I take every day, the different sessions that I open when I go to my newspaper, when I go to my technical forum, that they cannot be linked between each other. And this is very, very difficult if authentication is required. So if I don't need authentication, then you can imagine that I'll just go through an anonymizing web server every time that I want to go to this site. Then, apart from traffic analysis issues, to a certain extent, I'm pretty well protected. But if I need to authenticate, it's already impossible to do that. Because once I authenticate, I'm telling the server who I am. So we need unlinkability, and we need anonymous authentication. Okay? Again, why did I go through this whole thing? You could think that we don't really need anonymous authentication because all I need to do is authenticate under my pseudonym. It's not my real identity. I can sign up for the service under a false identity. We do it all the time. We have to fill in those annoying web forms that ask for our age and salary and everything we do. We just write garbage. So I could do that as well. But again, that's not enough. That doesn't solve the problem, the real problems that can occur with privacy loss. I'm going to spend just very few minutes talking about anonymous web surfing, and then I'm going to move on to the actual main part of my talk. This is a necessary infrastructure for anonymous authentication simply because if it's possible to track my identity through my IP address or through traffic analysis or through some other means, then it doesn't really help that the authentication protocol that I'm putting on top is anonymous, because it's possible to catch me below that level. There are two basic security goals in anonymous routing. The first is user anonymity. That basically means that I'm going to remove any identifying information from the packets that I'm sending. So if we forget about what's happening on the way, I'm just thinking about the server at the other end. The packets that it receives don't contain any identifying information about me. That's non-trivial, but not too difficult to do. The much more difficult task is that of unlinkability, and that's if we have an adversary who's able to actually look from a global level at the network, and they're going to see who's sending packets and who's receiving packets, without necessarily looking at content, and this is what the previous talk was about, then it's possible to link a client to a server. The aim of anonymous routing is to prevent that or to make it more difficult, or especially if the attacker has only a partial view of the network, it can be more successful. But in any case, I'm going to assume that I have such a mechanism. As I said, the user anonymity is not too difficult, and linkability is actually very difficult. To look at it graphically, I'm going to just take an abstraction and say I'm going to assume that someone has successfully implemented the level of anonymous routing. There's still more research to be done, but some progress has been made. And it basically works as follows. The clients will send their messages into some magical system, some internal network, which blinds the messages. It permutes them. It does other things, re-encrypts, decrypts and re-encrypts, and sends them on, but where there's not necessarily, we don't know the correlation between A, B, C, and alpha, beta, and gamma. We don't know the correlation, and so therefore it's impossible for someone just looking at this level to see which client is talking to which server. How is it achieved? There are a number of different methods. In the CD, there's actually the presentation is not there, but there's a whole paper which appears there, and you can find these references and also a general survey on how mixed nets work to get a feeling of how these things can be achieved. But at least to some extent they are reasonably successful. It's not simple, the problem's not solved, we're going to assume it here. Okay, the main point. Anonymous authentication, what is it? At least on a more formal and more technical level, and how can it be achieved? I just want to stress that if anybody has any questions, I should have said in the beginning, has any questions about what I'm talking about, please ask. I don't have any problems taking questions throughout the talk, especially if something is not clear or you think that I'm talking nonsense. That's also possible. So what's the high-level idea? It's what I mentioned beforehand. We want anonymous authentication protocol. So as a starting point, we know that to authenticate, you need to know something. So we have to somehow identify the user who's coming. So there has to be some information, something going on there. We have to know something about the person who's coming to authenticate, the user who's on the other side. Otherwise, we can't do anything. Anonymous authentication protocol has two properties. First, it's a general authentication protocol, meaning that the authenticating server knows that the user belongs to a given set of authorized users. Right? So it's sure that only an authorized user is getting in the door, but it's anonymous in the sense the authenticating server has no idea which of those users it is. Okay, that's the way we get around the contradiction. We need to know something, but we only need to know that it belongs to a set of users with a given set of permissions, and then once we know that, then we can allow the user in. We know its permissions, but we don't know which of the users it actually is. As I said, such a protocol has to run on top of an anonymous routing mechanism. We're going to assume that from now on. How do I define security for such a scheme? So first, as I said, it has to be secure authentication protocol, and this is defined just like any other authentication protocol. No unauthorized user should be able to fool the server into granting it access, except with very small probability. That very small probability is, you can think of it as someone guessing your password or guessing even your secret key for signing on digital signatures, these things can all happen with very small probability. Well, with your password, it depends how well you choose it. But so that's always a risk that can always happen in authentication protocols. It's something that we're not concerned about, because the probability of someone guessing your RSA secret key is so small that we just don't care about it. That's the first requirement, and has nothing to do with anonymity, but of course it is a requirement. The second one is as follows, and how do we formalize anonymity? This is a bit more tricky. I call this full perfect anonymity. I'll explain why after I give you the definition. Let's talk about the size of the set of users who are being considered. Okay, so we have, this can be all of the users who can possibly come into the system, or the users can be divided into different sets depending on their level of permissions. And as we'll see later on, for scalability reasons, we can also divide the users into sets for other reasons, for efficiency reasons. So let L be the size of the set of users being considered. Think of it as 100 or 1,000. We'll say that a protocol provides perfect anonymity if after the authentication takes place, so the server runs the protocol with the user, and now we're assuming that the server itself is the attacker. The server is trying to learn the identity of the user who's coming in. Then after the protocol is run, it can successfully guess the identity of the user with probability 1 over L at the most. Now, if you think about that for a moment, the server can always guess who the user is with probability 1 over L by just giving a random guess. That's always the case. So what I'm saying is the protocol is secure, and that's what's called perfect anonymity. It has nothing to do with breaking some cryptographic primitive, or there's no a greater probability of success. Basically, the only thing the server can do is just give a random guess. So that's a very, very strong level of anonymity. But sometimes it's actually useful to consider a more relaxed level. Why is that? Because sometimes we can get more efficient, more simple protocols that achieve a lower level of security, and it's something that I call verifiable anonymity. And here, it's possible for the server to cheat. However, if it cheats, then the user will know. So how does this definition work? The user may receive a special cheat message as output. So it runs this protocol, this authentication protocol with the server, and at the end of the protocol, either it gets a message saying, okay, everything's fine, you can continue, or it gets a message saying the server has tried to cheat you. If it gets a message saying the server has tried to cheat you, then obviously it just won't continue, it won't do anything more. It will either log out and, if it's optimistic, if the user is optimistic, try tomorrow or cancel the subscription. But the guarantee is that if the user does not get this cheat message, then once again we're guaranteed that the server's chance of knowing who the user is just 1 over L. So it's sort of, there's two cases. One, the server can actually cheat and know who the user is if it wants to, but then the user will definitely know that fact. Or the server cannot cheat, and then it's reduced to a random guess. Why do I think that this is sufficient? Because when I'm authenticating to some service, then that's the first thing that I do. I haven't done anything yet. All I've done is just try to log in. And if I found out that they know who I am because they've tried to cheat, they don't have to do anything else. I can automatically stop, log out, and nothing has been learned because I haven't yet done anything. All they know is that I tried to log in on that day. So I probably shouldn't try again 1 second later, but that's about it. Nothing has been lost, and therefore this is a sufficient level of security in most cases. So let's solve the mystery. Is it possible to achieve it, and how? Here's a really naive idea that sounds ridiculous, but it's one step towards the solution. Let's just issue all the users with the same password or the same secret key. Okay? Then obviously, when a user authenticates by presenting its password, the server has no idea who it is because everybody has the same password. Okay, it achieves perfect anonymity, but it's stupid. Why? Because you can't cancel anyone's account, right? If I need to cancel someone's account, then I have to basically I have to reset everybody's password, reset everyone's secret key, and the chances of the key being leaked inadvertently also becomes much, much higher. So this is not what we want. So what do we want? let's say we have a set of n users, or actually I should have used L users because that was the character beforehand. And I'm going to assume the public key infrastructure. I'm going to assume that the ith user has a key pair, which I denote SKI and PKI. For some public key encryption scheme, think of RSA. RSA is fine. So every user has a digital certificate. For RSA, they have a private key and a public key. And the server has a record linking every user to its public key. That's standard. In practice, obviously, what the server really just does is verify the certificate. It has a list of certificates, or has a list of users that are allowed access, and it checks the certificate which binds the user's name to the public key. There's no problem of cancelling user when we have such an infrastructure. All we need to do is just remove that record, remove that user's names from the list of authorized users. What we are going to assume, and I'll talk about this a little bit later because it's not so trivial or it can be problematic, we're going to assume that the users also know the public keys of the other users. Not just that the server knows who the users are, but also the users themselves. We'll talk about this a bit later. So here's the first attempt at a protocol, and it's surprisingly simple. It's not quite secure yet, but we'll see why, but it gives the flavor of how it can be done. So this seems like a very, very difficult problem, and I'm sort of stretching it out a little bit because the solution is actually surprisingly simple. At least this solution. The user sends a first message, which is just an anonymous request to connect. Okay, I want to log in. And what the server does is the following, and we'll have it graphically on the next slide. The server chooses a long random string, encrypts it, and sends it to the user. That's already a standard authentication type idea. The user just has to decrypt it and then send it back. Only someone who knows the secret key can decrypt, so only an authorized user can actually log in. The difference here is that the server doesn't encrypt that long random string under a single user's key. It encrypts it under all the user's keys in that set. And if you're worried about scalability issues already, then hold on, because I will deal with that. So it's going to encrypt that random string under all the users in the set and send it to the user. The user can only decrypt one of the ciphertexts because it only knows one key, but that's enough. It decrypts it, gets the message W and sends it back to the server. The server then checks that the person on the other side, the user on the other side, could decrypt and allows them in. Let's look at it graphically. So the user first sends an authentication request. The server chooses a long random string and decrypts it under everyone's public key and sends all of the ciphertexts back to the user. And the user then decrypts the ith ciphertext because that's the key that it knows. It knows one secret key only, and sends it back to the server. And the server accepts if the user could decrypt. So what's the security arguments here? As far as authentication goes, and again, it has to be secure authentication protocol. Without that, we haven't done anything. You can easily see that only one of the users in that set is able to log in, because if you're able to learn the value of W, it means you had to be able to decrypt at least one of those ciphertexts. Okay, so if you want to be able to log in, you have to be able to decrypt one of the ciphertexts. That means you have to know one of the secret keys. That means you have to be one of the legitimate users. Okay, again, if there are any questions, please ask them. If something isn't clear, please ask. So as far as, yes?
You said the server sends the same encrypted message for all of them.
Yeah. So that's exactly why this protocol is only a first attempt. Very good. In the next slide, I'll fix it. The protocol is only a first attempt because the server may cheat, and this is where we get to the anonymity issue. If it's true that the server uses the same random string in all of the ciphertexts, then we're fine, because all of the users will behave in exactly the same way. They'll get the same W. The problem is, and this is your question, that a cheating server may encrypt something different in every ciphertext. As a user, I'm only able to decrypt one ciphertext. I have no idea that the server did that. And if the server did that and I return the long random string that I got, then the server can know exactly who I am. So this is not enough. Again, we want a protocol that guarantees security from my end. All I need is for me to take care that I'm running the protocol correctly and I'm guaranteed that everything will be fine. Okay, I don't need to, I'm not going to trust the server in any way whatsoever. So the solution, and this is where it starts sounding difficult, we'll have a simple solution for this as well, is we want the server to actually prove that it encrypted the same random string in all of the ciphertexts. How do you do that? Well, for those familiar with more advanced cryptographic techniques, you can use things like zero-knowledge proofs. They exist in theory. They exist also in practice. But for this sort of problem, to prove that a set of users, a set of ciphertexts all encrypt the same random string is not going to be very practical. For 2 strings, if it's 2 ciphertexts, you could do it. But when you're talking about 100 or 1,000, it's going to be much, much too expensive. So we don't want to do that. Just as a note, really what we want the server to do is to prove to the user that it encrypted the same thing in all the ciphertexts. They can't decrypt because neither the server nor the user knows the other party's secret keys. So we're going to give a proof of encryption and quality, which is very, very simple. And as background, I just want to remind everyone that encryption is actually a probabilistic procedure. Okay? You can't, RSA is not secure if you just take the message and raise it to the power of E mod n. It's not secure in that way. You have to add random padding. So just as one example, if you take PKCS version 1.5 encryption, it works in the following way. You take your message, you add a couple of special bytes, but what's important for what I'm saying here is you add a random block of at least 8 bytes to the left of the message, and then that becomes the block X, which is raised to the power of E mod n. So that's how you do public key encryption. It has to be probabilistic. It has to use some block of random bytes. Otherwise, it just won't be secure. So with that background, let's talk about how it's possible for the server to prove that it encrypted the same value. What it can do is, rather than try to reverse the procedure, just show the user what it did in a forward manner. Okay? I can convince you that I encrypted a certain value without knowing the secret key, without knowing the private key, by just giving you showing you what I did in order to encrypt. Okay, I don't have to, if I'm the person encrypting, then I can always decrypt without knowing the private key by simply showing you how I encrypted. So what I can do is I can give you that random block that I used, give you the message that was encrypted, tell you which public key obviously that I used, and let you just re-encrypt and check what I did. And then you'll be convinced that I actually encrypted that specific message. In more detail, let's denote an encryption of a message W with a public key PK and using random padding R by EPK of W semicolon R. Okay, so R is not part of the message, not to be confused. R is the random padding, W is the message. That's how I'm going to denote it. And now what's important to note is that if I'm given a public key and I'm given a ciphertext and a plain text and the random padding, I'm basically given everything which I did to encrypt, then it's possible to check what is encrypted in that ciphertext. I don't need the secret key. All I need to do is just follow the procedure again, re-encrypt by following and doing exactly what the server did by an ambiguity of encryption, and it's a little bit technical, but it's not difficult to show. This ciphertext cannot be an encryption of anything else, and so the server cannot trick me. It can't give me some wrong random padding and somehow convince me of something which isn't true. A ciphertext locks the message inside because otherwise we wouldn't necessarily always decrypt correctly. So now we have a proof of equality. All the server needs to do is show me what it did to encrypt. Well, now we have a problem of how to use it. Because when can the server send me this proof of equality? If it sends it to me before I've decrypted, before I answer with W, then what's the problem? I'll know W even if I'm not authorized. Right? If it sends me all the information that it used to encrypt, then obviously I'll be able to learn W, and even if I'm not authorized. So that doesn't work. And if it sends me the proof of equality afterwards, then it may already have learned my identity. Because if it cheated and encrypted different values, then it's going to know who I am. But this is where verifiable anonymity comes in. What I'm going to do is I'm going to return W, but then I'm not going to proceed until the server convinces me and shows me that everything that it did is okay. So let's have a look at the full protocol. The user sends an authentication request. The server chooses a long random string W and encrypts that string, that same string under all public keys. It may cheat. That's what it's supposed to do. Okay? But it may cheat. I'm not saying it can't. The user decrypts the ith ciphertext because that's the only one that knows how to decrypt and sends back the value W. And the server then accepts the user and allows it access as long as it sends back the right string. But then it sends all of the random blocks that it used to encrypt those L ciphertexts. And the user just verifies that all of the ciphertexts that it got originally are actually encryptions of the same string W. And that's your proof that you asked about before. How can I check that the server is really acting correctly? This is exactly how I check it. And notice that it gives me exactly the verifiable anonymity that I talked about, because I'm not going to proceed to the next stage until I get those R1 to RL and check really that I'm safe. Yes?
So why can't sending R before receiving correct W?
Okay, so the reason is that if it does do that, then you have no guarantee of security of the encryption. Encryption is...
Even if you're not giving up the full message?
Yeah. And in fact, there are a lot of attacks. There was a previous paper that tried to do that where they said, we'll just encrypt W without random padding. But then it said, well, the only problem is we don't really know what encryption scheme to use because RSA is a problem. We know of RSA attacks if you encrypt the same message under many public keys. It's not a known plaintext attack. It's just a ciphertext attack. Given the public key, if you encrypt the same message under many public keys in RSA, then you can get back that message. So you have to have random padding. And once you have to have random padding, then if you give up the random padding, then you've lost at least your guarantees. We have no knowledge of how to prove that it's fine, and it probably isn't. So I have this theorem that says that if the encryption scheme is secure under chosen plaintext attacks, the most basic level of security for public key encryption, then the protocol is secure. For anyone who really wants to see actually a full cryptographic proof of security, it's in the paper in the CD, but I've put it in an appendix so as not to scare other people off. The basic idea is what I mentioned. It's secure authentication because only a legitimate user is able to decrypt one of the ciphertexts. So only a legitimate user can return W. And it gives anonymity because if this user does not get cheat, then it knows that all of the ciphertexts encrypt the same W, so it knows that the server has no way of knowing who it is. Again, all of the users would behave in exactly the same way, so there's no way of detecting that it's me and not someone else. What's the efficiency of this protocol? And here we get to more tricky issues. Well, the server overhead is a single encryption per user. With RSA and a small public exponent, that's not too expensive, depending on what L is. And I'll get to that soon. The client overhead is also to compute one encryption per user. That's for the check at the end. It has to re-encrypt, so it has to carry out that re-encryption. And one decryption. What's important about this solution is it uses only one decryption. And if we're talking about PKI and public key technologies, we'd like that decryption to be on a smart card, but it's only a single decryption. And one of the important things about this protocol, and this is when I started looking at anonymous authentication, this was really my goal. There are a lot of papers out there in the cryptographic world on anonymous authentication or anonymous credentials in general, and they have lots of nice features and lots of nice properties, but they all use very, very special purpose number theoretic problems and algorithms. The problem with such solutions is that if you want to actually deploy them, you can't use standard certificates. You need some different type of digital certificate, at least not one that you buy for RSA signatures or RSA encryption, because it's using something based on something completely different. And you also can't use standard smart cards, because standard smart cards do RSA and possibly some other things, but nothing that's being done in the anonymous credentials and anonymous authentication work until now. And this protocol allows you to use a standard PKI. So I already have a smart card. I already have a digital certificate for my smart card logon at work. Once I already have that, that's all I need to be able to, at least on an infrastructure level, to be able to run the protocol. And that I think is very, very important. If we're going to come up with cryptographic solutions to problems, we need to have them easily be deployed on an infrastructure level. In theory, there's no problem. There's no difference between RSA and between the bilinear Diffie-Hellman assumption, if anyone's aware of it. There's no difference on the theoretical level, but in the practical level, there's a huge difference, because I have an infrastructure for one, and I don't have an infrastructure for the other. But what about large or very large sets of users? Okay. If we're talking about thousands of users, then it's impossible, or in feed it's not impossible, it's infeasible to expect a server to carry out thousands of encryptions per authentication. If you think about the user, it's actually not an issue, because it's not a big deal for the user to encrypt 1,000 times on a PC. If you think about the algorithms for encryption, decryption, and RSA at least, 1,000 encryptions on the PC would probably take no more time than one decryption on a smart card. In fact, it could possibly even be less if you're using small exponents, small public exponents. So in terms of scalability, it's a problem on the server side. But we can use something which is called k-anonymity. And k-anonymity means it's something which is used a lot in the privacy world. And it tells you that I can release information, I can release databases, as long as it's guaranteed that I may be able to locate a user, but only within a set of k others. So no one can know exactly which record in the database refers to me, but they can know that I'm one of these k records. In general, actually, I don't like k-anonymity, because it may be that you can't, you can only know that I'm one of the 100 database entries. But it may be that all of those 100 database entries have AIDS, and so it doesn't really help me that you don't know which one I am. Whereas what I'm talking about is a higher level of k-anonymity, where I say that you can't locate me within 100 random users in that database. And that's a much, much stronger guarantee. And the way to achieve this is, rather than use all of the users when I'm authenticating, I'll choose a random subset of, say, size 100. In fact, smaller would even possibly be reasonable. That's something which is already more of a policy level than a technical level. But I'll choose a set of users, and I'll hide within that set of users, of 100 users, and that would suffice. So you wouldn't be able to link me because of that. An implementation issue that arises then again is, well, the protocol, as I mentioned, assumes that all the users know the other users' public keys. That assumption is implicit in that I have to re-encrypt. And if I have to re-encrypt, I have to know the other user's public keys. And the question is, how is this accomplished? Because let's think of the following malicious server. If the server is going to post all of the public keys of the users, then it can actually post 90% of them to be fake. And when I choose my random subset of 100, maybe I'm really choosing 90 fake and only 10 real. So that's an issue, and that's an issue that has to be solved. You would need to have some external source, or to have a fixed set of users ahead of time that you're going to decide to be together and keep your anonymity at that level. What about full anonymity? What I gave you until now was a protocol for verifiable anonymity, which said that the server may be able to cheat, but then I'll detect it. What happens if you want to prevent all cheating? And here is a very nice trick, which is based on something called ring signatures. Ring signatures is a new primitive which was proposed by Rivest, Shamir, and Talman. It's the same Rivest and Shamir as in RSA, but Talman is, Yael Talman was a master's student of Adi Shamir, who did this in her master's thesis. And it's a way of signing on a message so that you have this ad hoc ring of users, and you sign on the message so that only one of the users in the ring, it's really just a set of users, could have signed on the message. But it's impossible for anyone verifying to know which user it was. Okay, so it sounds very similar to what we're doing. Interesting, the rings can be formed by anyone on their own, and this is an interesting twist. The initial application they suggested this for was how to leak a secret. What does that mean? Let's say I'm a member of Congress, and I want to leak something secret from the government to the press, but I want the press to be sure. I want to convince the press that I really am a member of Congress. And I don't want to let them know exactly who I am, because then I'll be in trouble. So what I can do is form a ring of all the users, all of the members of Congress with their public keys, their RSA keys, and I can sign on that message without even needing the consent of those other users. So when Adi Shamir presented this at the crypto conference, someone got up in the audience afterwards and said, if you ever wanted to give me a good reason why not to use RSA, that's it. Because basically what that means is that anybody here who has an RSA public key, I can sign on something that's everybody in the world will know it's either me or you. And there's nothing you can do about it, and you'll automatically become suspect. So that's the initial application that they were thinking of for ring signatures. But I'm going to use it for something different. It uses, again, you can use regular RSA. It requires one decryption and an additional encryption for the rest of the users, so it's the same complexity as in my previous protocol. And just to get a feeling of how it works, the basic idea is, let's say you have 6 users, then in order to sign on a message, you have to close the ring. The way you can close the ring is only one way. You can go forward 5 steps, but you can't close it by going forward a 6th step. In order to close the ring, you have to go backwards. In order to go backwards, you need to know the secret key. It doesn't say anything. It's actually quite a complex solution, but just sort of to give some sort of feeling how it works. And this can actually give anonymous authentication in a very, very nice way. You can incorporate it into SSL very, very directly. SSL with client authentication, for those of you familiar, works by having the client sign with a digital signature on all of the handshake messages until that point. That's the way client authentication works. So all you need to do to get anonymous authentication is just use a ring signature instead of a regular signature. That's the only difference that you need. So just change the encryption, the signature, the signing function call in SSL client authentication, and change that to a ring signature, and you're done. And you automatically have anonymous authentication. Secure authentication is, again, from the properties, the unforgeability properties of the ring signature, and anonymity comes from the anonymity of ring signatures that we talked about. So this solution is very, very nice. It's a new application of ring signatures, and it's nice because it just gives you a quick, direct plug-in to SSL with client authentication, and then everything is fine. To compare the protocols, well, actually, the first protocol that I showed you has higher bandwidth than the ring signature, because the ring signature itself is just 1 block length. It's no more. Its advantages are it's really simple, so I can actually show you and convince you that it's possible to get anonymous authentication. But ring signatures, I just sort of hand-waved and told you they exist. I didn't tell you how to do it, and it's much, much difficult to show you that. And also the advantage, you can use any encryption scheme, and it doesn't have high requirements, whereas ring signatures has other stronger requirements, but I'm going to ignore that for now. I want to talk a bit about revocable anonymity. Because in the protocols that I showed you now, there's no way to revoke anonymity. All the users behave in exactly the same way. And we want to be able to ban access to users who misbehave, hostile users, and in many cases we do need help to do that. Again, I'm assuming a court authority, and the court authority is able to revoke anonymity, but only that authority. There exist solutions to this problem. Again, the solutions that were until now used completely different cryptographic primitives, ones that are not deployed in practice and therefore are an obstacle. I'm working on this problem. I don't yet have a full solution. What I do have is a solution that does require a special purpose smart card. So for example, you need to use a Java card and put some a special purpose Java applet. Therefore, it's not as easily deployed, but it does still use standard RSA and standard PKI. So it's sort of in between in terms of deployability issues. Here's a first attempt. We give the court authority a public-private key pair, and the user, when it wants to authenticate, will encrypt its identity under the court's public key. Then in order to revoke, all the court needs to do is decrypt and see whose identity that is. Obviously, this is ridiculous because the user can cheat. It doesn't need to actually send its correct ID, and or can even send someone else's ID. And the way we do that is by having the smart card. I'm just going to go through this very briefly. We have the smart card do that operation, and we model the user actually as a man-in-the-middle adversary. So the user here is trying to somehow force the revocability to fail. So the smart card and the server are going to be working, and the user is actually going to be modeled as a man-in-the-middle adversary. But there's more. I'm going to skip over that. There's more details in the paper. What about passwords? And this is the last extension I'm going to talk about. What if I don't have a PKI? Okay, so this becomes much more difficult. And if I want to use symmetric keys or passwords or one-time passwords, then, or even biometrics, which is quite wild, right? Doing anonymous authentication using biometrics, it seems to be much more difficult. But here's the following high-level idea. The first step is to use standard authentication. Okay, so I send my password, or I run my fingerprint, or I use my symmetric key. Once I've authenticated, I now register a public key with the user, and then with the server, and then I disconnect. I disconnect, and then at a later stage, I reconnect using that temporary public key and using the same protocols we've seen beforehand. For authentication, there are no problems. That works fine. For anonymity, it's preserved as long as the server can't link the anonymous authentication protocol taking place later with the user who just disconnected beforehand. So you need to either somehow register that key earlier, or you need to use time slots. It gives you a lower degree of anonymity than we had beforehand, a far lower level. And it also intensifies the problem of how do I know the other user's public keys. So we want to be able to register these temporary keys on an external website that's not run by the same server, and we'd like to assume no collisions. So in conclusion, what I started with is that privacy is far more than just the right to be let alone. The right to be let alone, I'm not belittling the importance of it, but the emotional distress is only a very, very small part of the problem. The bigger problem is when our information is actually used against us and not just revealed in terms of what people learned against us. And what we need for that is unlinkability. And anonymous routing can be used to get that on a basic level, but once we need to authenticate, then we lose that as well. So once we have to authenticate, then all the anonymous routing in the world doesn't help us at all. And if authentication is needed, then surprisingly it's possible to achieve anonymity. And we talked about two protocols, one which is very simple and gave verifiable anonymity, one which is more complex cryptographically, that was the ring signatures, but it can actually very, very easily be deployed by just modifying the signature operation in SSL client authentication. We talked a bit about revocable anonymity, and there's definitely much more research to be done on that side, because for now we only have a partial solution. And I think one of the very interesting questions is, can full anonymity be achieved if you're only using symmetric techniques, if you're only using passwords? And we don't have an answer for that question. I think it's definitely an interesting area for future research. That's basically what I said, and thank you very much for your time. If there are any questions.